Last week, we have learned about different types of sampling methods, about convenience sampling, about voluntary response sampling. Both are biased. They bring bias in research. We also have learned how to do a simple random sample. This week, we will focus on random sampling by learning more about samples. Suppose that I have this exact research question. How many students in Ontario high schools have smoked cannabis in the last year? How many percent of all students? We don't know. We don't know the answer. Knowing the right answer, the exact percentage of students in Ontario who smoked cannabis would be knowing the parameter. A parameter is an important concept. It is a number that describes the whole population. And unless we ask every member of the population, we don't know the true value of the parameter. This is why we have to select a sample and guess what the parameter is from this sample, because we do not have access to the whole population. So in social science, we don't have the means to survey the whole population. We do not have access generally to whole populations. We can't afford, we don't have time. So we work with estimations of the value of the parameters we're looking for. We do that by selecting samples the best we can and working with statistics. A statistic is an estimation of the parameter. It comes from a sample, and ideally, it is as close as the parameter as possible. So you have 4 words to remember. A population, you know what it is already, and a number that describes a population is called a parameter. Both start with letter P. A sample is a fraction of the population you work with, and the number that describes a sample is called a statistic. Both start with letter S. But even with random sampling, you will never, or almost never, get the same number, the same statistic in 2 different samples. Statistics change from sample to sample, and this is normal. Let's see an example. These are real numbers that were obtained a few years ago about answering that question. How many percent of Ontario high school students have smoked cannabis in the last year? So a sample was taken by the Centre of Addiction and Mental Health of Ontario. This sample included 4,894 students. That's a pretty large sample. And from that sample, it was discovered that 1,434 students had used cannabis in the last year. So I have here, I don't have a percentage, I have a count, but I can turn this count into a percentage by cross-multiplying. If I cross-multiply, I obtain here 29% as a statistic. 29% of Ontario students in my sample have used cannabis in the last year. This number comes from a sample, so it is a statistic. We can use that sample, 29%, as an estimate of the parameter. And remember, we don't know, we never know the parameter. It's an unknown number. So we really hope the statistic we have is representative of the parameter. But imagine we select another random sample of 4,894 Ontario students. We would probably get a different number, a different count of weed smokers, which would lead to a different percentage. So from sample to sample, even if these samples are randomly selected, the number changes. It's normal. And this is called variability. This is an important word for you to know. So, good random sampling will help you avoiding bias in research, but it does not avoid having variability in research, having this variation in number from sample to sample. This is happening. It's normal. So how do we do to get rid of variability or to reduce variability, to reduce this chance of having a very different number from sample to sample? The answer is we have to select large samples. A large sample will likely give a statistic that is closer to the parameter than a small sample. So we have seen two kinds of errors that happen when we do estimations of the parameter. The first type of error, we have seen it last week, it is called bias. It's the consistent deviation of the sample statistic from the parameter. In other words, it is the systematic overestimation of the parameter or the systematic underestimation of the parameter. And to try to avoid bias, we use random sampling. The second type of error, variability, describes how different from each other would be different statistics if we take multiple samples. So we want variability to be as small as possible. A small variability means you can trust the results of your research. A large variability means you really can't trust your results because in different samples, they would be very different from each other. So we have to reduce variability in research, and to do so, we increase the size of the samples. We take large samples. To quickly summarize what I have said so far, in research, in social science research, we want to reduce bias, ideally to eliminate bias. To do so, we use random sampling. And we want to reduce variability. We can't eliminate variability, it's impossible. But we want to reduce it as much as possible. And to do so, we include as many subjects as we can in our samples. We use large samples. Another important concept about sampling, about random sampling, is the margin of error. And it is calculated in percentage point, plus or minus 5%, plus or minus 1%. The plus or minus is very important here. It is part of the margin of error. The margin of error tells how close your estimate about the population, and estimation is a statistic, how close your statistic comes to the truth. The truth is the parameter. You have seen these kind of news in your newspaper or newsfeed, something, for example, like 22% of Canadians oppose the obligation of wearing a mask in public. Margin of error, plus or minus 6%. You see these kind of results of polls. There's always a margin of error when you take a random sample to do research. And we want this margin of error to be as small as possible. Because a small margin of error means you probably are close, your statistic is probably close to the parameter. This is what we want. We want good estimations. So a margin of error of plus or minus 5% would mean if I take 100 random samples in my population, 95% of them, so great majority, would give me a result within plus or minus 5 percentage points of the parameter. So it's good. A margin of error of plus or minus 2% means if I take 100 random samples in my population, 95 of them would give me a result, a statistic, within plus or minus 2 percentage points of the truth of the parameter. Oh, we prefer that. We want a small margin of error because it's a good estimation of the parameter. And the margin of error is directly linked with the sample size with random sampling. The bigger is your sample, the smaller is the margin of error. So margin of error is a reflection of the variability. We want a small margin of error, we want small variability, so we use big samples ideally. There is a very simple formula to calculate the margin of error, and what you need here to calculate it is the size of your sample, the number of subjects included in your sample. The formula is the following: 1 on square root of n, n being the sample size. So for a sample of 3,000, for example, I will do 1 on square root of 3,000, 1 divided by the square root of 3,000. The square root of 3,000 gives me about 55, 54.77. So I do 1 divided by 54.77, which gives me 0.02. Now, how many percent is that? Is 2%. So my margin of error here for a sample size of 3,000 will be plus or minus 2%. Not plus or minus 0.02, no. Plus or minus 2% here is my margin of error. If you want to calculate it as an exercise for a sample size of 100, you will do the following. 1 divided by the square root of 100. This is 1 divided by 10. The square root of 100 is 10. 1 divided by 10 gives you 0.1, which is 10%. So the margin of error for a sample size of 100 will be plus or minus 10%. So you see here, you have a much smaller sample with 100, you have a much bigger margin of error. And now you have everything you need to write a confidence statement. To write a confidence statement, you need 2 things. You need a statistic, and the statistic needs to be in percentage, not in count, in percentage. And you need a margin of error that is also a percentage. If you have these 2 ingredients, you can write your confidence statement. And we will do one with the following example. It's a real-life example. Gallup, last June, asked American citizens the following question. Do you approve or disapprove the way Donald Trump is handling his job as president? And the result of this poll indicated that 39% of Americans said yes, they approve. It's not 39% of all Americans here. It's 39% in their sample. Of course, they did not ask all American citizens. And they said their margin of error is plus or minus 4%. So you have the 2 ingredients you need here to write a confidence statement. You have your statistic in percentage, 39%, and you have your margin of error, plus or minus 4%. So a confidence statement goes like that. I am 95% confident. The 95% here never changes in the confidence statements we will learn this semester. It's always 95%. We call it a confidence interval. So I am 95% confident that between 35% and 43% of Americans approve Donald Trump. So where did I take these 2 numbers, 35% and 43%? It comes from my statistic. My statistic in my sample was 39%. But I cannot apply it to the whole population. I have to play with my margin of error here. So 39% minus 4%, my margin of error, gives me 35%. And 39% plus 4%, my margin of error, gives me 43%. This is where I took these numbers. So my confidence statement goes like this. I am 95% confident that between 35% and 43% of Americans approve the way Donald Trump is handling his job as a president. That's my confidence statement here. I cannot claim, as you often see in the newspaper, 39% of Americans approve Donald Trump. No, I'm not sure about this number, 39%. I did not survey all American citizens. I surveyed a sample. So I cannot claim 39% of Americans approve something. And also I have a margin of error. And I'm not even 100% sure. I'm only 95% sure of my numbers. So in research, in surveys, when you have a random sampling, you're never totally sure your number is exactly the truth. It comes from a sample. It has variability. It has a margin of error. We'll do a last example here. According to a study held 5 years ago among a pretty big sample of 12,000 randomly selected Cégep students, there's a result here. 35 of them in the sample, 35 of them report they often suffer from anxiety. You cannot claim 35% of Cégep students often suffer from anxiety. No. There's a margin of error. There's a confidence interval here to work with. We would see that in a newspaper. 35% of Cégep students suffer from anxiety. No, there is an interval. There's numbers to work with. So we'll do a confidence statement for this one. We have a statistic here in percentage. It's 35%. And we do not have a margin of error. We have a sample size, but we can calculate the margin of error with the sample size. 1 on square root of n being the sample size. 1 divided by square root of 12,000 gives me 1 divided by 110. It gives me 0.009, which is 0.9%, we will round up the number, plus or minus 1% is my margin of error. It's a very small margin of error, which is good in research. Very small margin of error. We like this because we had a large sample. So my confidence statement would go like this. I'm 95% confident. You're not sure. You're not 100% confident. You are 95% confident that between 34 and 36% of Cégep students often suffer from anxiety. So here you see you have a small margin of error, plus or minus 1%. So you don't have a big gap between 34 and 36%. You can trust the result of such a research because the margin of error is very small.